Perhaps due to an extremely varied history, sacred geometry seems to now have as many interpretations as there are interpreters. Some view it as a simple mathematical curiosity. Others believe it to be a system of philosophy that is intrinsically tied to the very existence of this universe. Some have approached it with strict mathematical analysis and rigor. Others have delighted in the philosophical implications that seem to be whispered through this language of numbers and geometric form. Architects have built monuments to the gods based wholly on its proportional precepts. And composers have created entire symphonies to convey its mathematical scripture in sound. Yet the majorities of people pass into and back out of this life without ever being aware of the patterns that build the foundation of the matter in this universe. Although many ancient cultures were clearly familiar with sacred geometry, it is commonly believed that the ancient Egyptians may have been the first culture to recognize and employ its mathematical proportions. It is believed that the annual flooding of the River Nile, pictured here, wreaked havoc with land ownership boundaries on a yearly basis. Amongst other difficulties, the continual destruction of land ownership boundaries made accurate taxation a near impossibility. A systematical approach that could efficiently survey the land by using only a single reference point was required, and thus geometry was born. Geometry, interpreted literally, means earth measure, or to measure the earth, and the practical application of needing to survey land on a regular basis may have spawned the first true mathematical system. It is commonly believed that the first geometric revelation that occurred to the Egyptians was the fact that a rope with 12 knots tied in its length at equal distances from one another could be easily employed to generate a 90-degree angle. By bending this rope at the 3rd knot, and then bending it again at the 7th knot, the 12th knot can be brought around to touch the 1st. If the 3 sections of rope are pulled taut, the bend created at the 3rd knot forms a perfect 90-degree angle. As long as a single point of reference could be determined, such as direct line of sight to a permanent marker beyond the bounds of the flood plain, the 90-degree angle established by this procedure was all that was required to survey the land with empirical certainty. This common operation of the Egyptians, which later took on the same holy significance as laying the foundation stone of a temple, was in fact the first known usage of the Pythagorean theorem, and was put to use by the Egyptians thousands of years before the Greek Pythagoras ever lived. By the pinnacle of Egyptian culture, every aspect of life had been imbued with spiritual significance, and geometry was no exception. Geometry, besides being used for surveying land, became a fundamental basis for the creation of all forms of craft. Strict geometric canons were developed, declaring rigorous guidelines for the creation of architectural plans, wall carvings, sculptures, jewelry, and even for the creation of ceremonial vessels. Amongst the proportions that the Egyptians deemed to have sacred significance is the square root of 3. Although initially seeming to be a somewhat obscure number, when we look at how the square root of 3 can be generated in geometry, its significance becomes clear. Using a compass, we first plot a circle. We then move the point of our compass to any point on the circumference of the circle just created. And without changing the width of the compass, we create another circle. We have now created 2 circles of equal radius that overlap one another evenly. Note that the circumference of each circle cuts directly through the center point of the other circle. The oval space that is shared by the 2 circles has been labeled the Vesica Piscis. And if its width is taken to measure 1, then its height happens to measure approximately 1.732. We can only approximate the measurement of the vesica's height because, like pi, the square root of 3 is an irrational number. This means that it has an infinite number of integers after its decimal point. Any irrational proportion that can be easily generated by a geometric shape, such as pi or the square root of 3, was considered to be of special spiritual importance to the Egyptians, as well as their geometric heirs, the Greeks. To continue working with our vesica, we can connect the two center points of our circles with a line, and then connect the endpoints of this line to the vertical points of the vesica Pisces. We then find that we have created two equilateral triangles within the vesica. Note that all of the sides of the two triangles are equal in length to the horizontal axis of the vesica. Thus, the proportional relationship between an equilateral triangle's edge length and its height must be 1 to 1/2 the square root of 3. Now, if we extend the edges of the two triangles just created, we find that the lines divide the two circles' circumferences into 6 equal sections. If we connect the points where these lines touch the circumferences of the circles, we find that we have generated a perfect hexagon. Naturally, another perfect hexagon comparable to the one shown on the left can be similarly created in the circle on the right. As can be noted from the diagram, a hexagon is nothing other than 6 joined equilateral triangles. We can also easily see that in any perfect hexagon, if the edge length of the hexagon is taken to measure 1, then the height of the hexagon from the midpoint of one side to the opposite side measures the square root of 3. Moving into three-dimensional shapes, we find that the perfect cube also contains the square root of 3. If we draw a line from the lower left corner in the front of the cube to the upper right corner in the back of the cube, and assume that the edge length of the cube is equal to 1, then the transversal that we have just created measures the square root of 3. This proportion is true for all perfect cubes, no matter what size or scale. The tetrahedron is another three-dimensional shape that contains the square root of 3. Along with the cube, the tetrahedron is classified as one of the 5 Platonic solids. In the Platonic solids, every edge length, every angle, and every face is equal throughout a given polyhedron. The tetrahedron in particular is volumetrically speaking the smallest and the most basic of the Platonic solids. Consisting of just 4 equilateral triangular faces, the smallest number of sides possible to enclose a three-dimensional space. In order to understand how the tetrahedron relates to the square root of 3, we must understand that in any regular polyhedron, there are 3 spheres that are commonly used to define the shape. The insphere is a sphere that shares the center point of the polyhedron and whose surfaces touches the center point of each face. The intersphere is a sphere whose outer surface touches the center point of each of the tetrahedron's edges. The circumsphere is a sphere whose outer surface just touches the vertices of the polyhedron, thus completely enclosing it. In the tetrahedron, if the radius of the insphere is taken to measure 1, then the radius of the intersphere measures the square root of 3. Also, if the radius of the intersphere is taken to measure 1, then the circumsphere also measures the square root of 3. Thus, the 3 spheres of the tetrahedron form a perfect square root of 3 progression. Yet another three-dimensional shape that contains the square root of 3 is known alternately as the cuboctahedron, the Dymaxion, or, as we will refer to it here, the unified vector field. The unified vector field is classified in geometry as one of the 13 Archimedean solids. The Archimedean solids are similar to the Platonic solids, but differ in that their faces can consist of more than one type of regular polygon. As can be seen in the diagram, the unified vector field has 8 triangular faces and 6 square faces. What is completely unique about the unified vector field is the fact that if we draw a line from its center point to any of its vertices, we find that line to be of equal measure to the length of any edge. No other polyhedron can claim to possess this type of equidistant lattice. Assuming that the edge length of the unified vector field measures 1, then we find that the distance between the center points of opposing edges measures the square root of 3. Another way of observing this same relation is to note that if the edge length of the unified vector field equals 1, then the diameter of its intersphere measures the square root of 3. So, we can see that the square root of 3 is inseparable from certain regular geometric shapes. In the two-dimensional plane, the square root of 3 is contained in the vesica Pisces, as well as the two regular polygons generated by it, the equilateral triangle and the regular hexagon. In the three-dimensional plane, the square root of 3 can be found in the cube, the tetrahedron, and the unified vector field. It is only in the last 50 years that we as a race have gained the ability to peer into the structure of the very matter of this universe. Using modern technologies, we have begun to plumb the depths of atoms and molecules, and what has been found is that an inordinate number of molecules employ geometric arrangements in their atomic structures. Amazingly, the square root of 3 proportion, heralded by sacred geometry for thousands of years as a sacred number, is an inherent aspect of many of these structures. Some of the most common substances to us have atomic and molecular structures based on the square root of 3. Here we see a structural section of a water ice crystal. Note the tetrahedral arrangement of the oxygen molecules, pictured here in blue, which are tied to one another by hydrogen bonds, shown here in yellow. The matrix formed in water ice is a series of nested tetrahedrons, with stacks of smaller tetrahedrons forming encompassing tetrahedrons. It is also interesting to note that while on a microcosmic level, water ice forms along a tetrahedral lattice, on the macrocosmic level, such as is found in the common snowflake, the tetrahedral lattice creates an obviously hexagonal pattern. As noted earlier, both the tetrahedron and the hexagon are intrinsically tied to the square root of 3 proportion. When boiled, water also forms hexagonal cells. These hexagonal cells, pictured here in a false color image, are commonly referred to as Bénard cells, after the French physicist Henri Bénard, who discovered them at the beginning of the 20th century. Bénard found that when very thin layers of water are evenly heated, the resulting convection currents form hexagonal cells. In these convection currents, heated molecules rise near the center of the cells, and cool molecules descend along the edge of the cell walls. Water appears to be able to maintain its square root of 3 patterns no matter what state it occupies. Many noteworthy structures can also be found in pure metals, or metallic crystals. Metallic crystals differ from other substances in the fact that their molecules tend to be very densely packed, and as we shall see, this close-packed aspect oftentimes leads directly to the formation of lattices based on the square root of 3. 3 basic lattices are found throughout metallic crystals. The first, known as face-centered cubic, can be found in metals such as calcium, aluminum, and strontium. Note the obvious cubic structure. The second type of lattice found in metallic crystals, labeled bodied centered cubic, can be found in such metals as lithium, potassium, rubidium, cesium, barium, and sodium, also known as common salt. Once again, an obvious cubic arrangement appears. But note that with this lattice in particular, the bonds between individual molecules follow exactly the square root of 3 transversal. Whereas with face-centered cubic lattices, the molecules merely imply the square root of 3 via their overall cubic form, in bodied-centered cubic configurations, the square root of 3 is an inherent aspect of the crystal structure. The final metallic crystal structural configuration is known as the hexagonal close-packed lattice. It can be found in such metals as magnesium and beryllium. As the name implies, the hexagon, and thus the square root of 3, is the geometric basis for this molecular arrangement. Metallic crystals and water ice are not the only common substances in which square root of 3 lattices can be found. Here we see the molecular structure of sodium chloride, also known as common table salt. Its formation can be aptly described as two interpenetrating face-centered arrays, one of sodium ions and the other of chloride ions. Many substances arrange themselves in hexagonal patterns, and this is particularly true for the substances known collectively as the network solids. All network solids possess atomic arrangements that form indefinitely extending three-dimensional networks. The hexagon, due to its ability to be arranged in regularly divided grids, is just the right geometric form to create such indefinitely extending networks. To find an example of such a hexagonal matrix, we need only look so far as the common mineral quartz. This diagram shows the top view of quartz's molecular structure, and represents the form of quartz that is found as an abundant component of ordinary sand. Along with other substances, graphite and cadmium chloride share the hexagon as their fundamental molecular unit. Graphite forms flat layers of interlocked hexagons, which gives each layer substantial strength in 2 dimensions, but allows these layers to easily shear off from one another. This soft yet hard characteristic makes graphite the perfect material for making writing implements, as well as dry lubricants and polishes. The carcinogen known as cadmium chloride, on the other hand, forms interlocked layers of adjacent tetrahedrons. If we isolate a single layer of either cadmium or chlorine atoms, we find the same regular hexagonal division of the plane as we discerned in graphite. However, because cadmium chloride's hexagonal planes are tied to one another with bonds following stable tetrahedral geometry, cadmium chloride will not cleave into layers as graphite does. Here we see the atomic arrangement of carbon tetrachlorine, which possesses an obviously cubic atomic arrangement, accented in red. However, if we connect the 4 chlorine atoms, shown as yellow spheres, we find that a tetrahedron is formed within the body of the cube. This inner tetrahedron is imaged here in blue. This overlapping arrangement of both tetrahedral and cubic structures allows us to define the structure of carbon tetrachlorine as both tetrahedral and cubic, or complex tetracubic. Nature seems to have noted the interchangeable relationship between the tetrahedron and the cube as well, as we find in many substances complex combinations of cubic and tetrahedral matrices. Diamond, formed of elemental carbon, is the absolute hardest substance formed by nature, and is also a superb example of a combined cubic and tetrahedral lattice. We see its structure here with a red, face-centered cubic structure superimposed on it. The outermost atoms in Diamond's lattice form a perfect, face-centered cubic structure. However, if we instead accent the tetrahedral organization of the form, we find that it is similar to the structure of water ice. As with ice, Diamond consists of stacked tetrahedrons, but in the case of Diamond, the pyramid of tetrahedrons is laid on its edge, and thus fits perfectly into an enclosing cube. Therefore, Diamond's form can be concurrently considered both a perfect face-centered cubic design and a perfect nested tetrahedral structure. Another excellent example is found in calcium fluoride, shown here. The yellow spheres in this diagram represent calcium atoms, whereas the light blue spheres represent fluoride atoms. The light blue fluoride atoms fall at the center of a tetrahedron formed by 4 surrounding calcium atoms. The 4 points of each tetrahedron touch either the corners or the center points of the faces in an enclosing cube, shown in red. When the tetrahedrons for each fluoride atom are added, we see the complexity of the overall design. The 8 light blue fluoride atoms not only fall at the center of 8 tetrahedrons, but they also form a secondary cube that is exactly 1/2 the size of the surrounding cube. Other substances with square root of 3 lattices abound, but the preceding examples suffice to show that the square root of 3 is an inseparable aspect of many common substances. The next logical question that begs to be answered is why this might be so. The apparent answer to this question is twofold. First, one must be familiar with what is commonly referred to as close packing. Close packing is a geometric exercise in which we observe the maximal number of similar spheres that can be packed into a given space. On the two-dimensional plane, a single sphere can be surrounded by 6 similar spheres, which effectively creates a hexagonal distribution. There is no other way possible to close pack more or less than 6 spheres around a single sphere if all of the spheres are geometrically similar. In 3 dimensions, however, 2 possible close pack configurations are possible. If we build on the hexagonal pattern that we have just created, we can add first a layer of 3 spheres, and then another layer of 6 more spheres. The resulting arrangement is a close packed group of 17 spheres, and it coincides perfectly with the atomic arrangement that we saw earlier in metallic crystals such as magnesium and beryllium. In the second possible arrangement of close packed spheres, we begin with a layer of 5 spheres. Atop this, we add a layer of 4 spheres, and then a third layer of 5 spheres, similar to the first. The resulting arrangement corresponds exactly to the face-centered cubic structures that we have witnessed in several atomic lattices, including aluminum, sodium chloride, and diamond. The third type of common atomic lattice mentioned earlier was called bodied-centered cubic. If we interpret this arrangement as a close-packed pattern, we find that it comes extremely close to fulfilling the requirements to be considered close-packed. That is, although the body-centered cubic lattice is not a perfect close-pack arrangement, it is a very tightly packed formation. Considering the prevalence of face-centered cubic, bodied-centered cubic, and hexagonal close-packed molecular structures, it is safe to say that close packing is a common aspect of molecular formation. Although we can't say that close packing is the cause of how molecules form, it would seem that nature tends to fill space with atoms in the most compact and efficient means possible. To answer why matter would tend to organize itself in close-packed patterns, we must turn to the work of Sir William Rowan Hamilton, an alcoholic Irishman who lived in the early 1800s. Sir Hamilton was a child prodigy and mathematical genius, and his work is credited with laying the foundation for the modern physical study known as quantum mechanics. Amongst other mathematical discoveries, he discovered what has been labeled the principle of least action, which states that a given substance will structure its molecules in such a manner that the lowest possible potential energy is achieved when its formation is complete. To effect the state of lowest potential, an atom must structure itself in such a manner that it is able to resist external stress readily. In order for a material to share stress across its entire structure, the arrangement of that material's atoms must have elements that are equally spaced from one another. By forming in regular geometric polygons, every point in a given structure flexes to resist force applied to any point in that structure. The triangle pictured here is physically the strongest form possible in 2 dimensions, not only because all of the points in the structure will share external stresses equally, but also because it has the fewest number of points required to create a regular polygon. The fewer the number of equally spaced points that are found in a lattice, the stronger that lattice will be. Because close-packed structures meet these requirements better than any other form, we find that nature chooses to employ them over and over again. Thus, we begin to get a glimpse of the great logic that lies behind the prevalence of the square root of 3 and its related geometric forms in the foundation of the matter in this universe. But where does this leave us? What can we do with this information? We can employ it in our art and architecture, as have so many cultures before us. We can use it scientifically to understand more about the physical forces that shape this universe, as have the physicists since time immemorial. And perhaps, most importantly, we can teach it to our children, so that they too may understand that we do not live in a cold mechanistic cosmos, but that we live in an indescribably complex world that is based on a few beautifully simple principles. It is this sense of awe and respect for that which surrounds us and gave birth to us that is sacred geometry's greatest gift.